people here. I think we can figure it out. Anyway, thank you. So without further ado, without further pause, I would like to get into discussing some science on the surfaces of Ceres and Earth and other planets in the future. So, as Brittany mentioned, I've been here for about a little more than 1.5 years, coming up to 2 in the spring. And I started at Georgia Tech by giving a talk on Dawn results at Ceres and some of the work that I'd done for my PhD. So I thought it'd be fitting now to kind of close the book a little bit on Dawn and refer to the final results that I have been involved with from the Dawn mission for Ceres and the implication for planetary and terrestrial geology and geomorphology and exploration going forward. And a lot of these are recently came out of the final extended mission that the Dawn spacecraft undertook at Ceres that were published in a series of Nature journals that came out in late summer and early fall of this past year, and how some of those projects have informed what we're doing now at Georgia Tech in terms of Brittany and I in planetary geomorphology. So appropriately, I wanted to call this the final harvest from Dawn, spotlight on Occator crater, a very famous location. So a little bit of cosmic context. For those of you who have seen my slides before, you may recognize a few of my introductory pieces, but I love them too much to give them up. So I appreciate your patience. And for everyone else, the dwarf planet Ceres is the largest asteroid in the main belt between Mars and Jupiter. In and of itself, it accounts for around 1/3 of the mass of the entire asteroid belt, all wrapped up into one spherical dwarf planet. But despite its large size, which is around 1,000 kilometers across, or about as wide as the state of Texas, it has a mean density of only around 2.16 grams per cubic centimeter, which is much lower than that of the terrestrial planets, and is even low for an asteroid of this size, despite being fairly typical of small asteroids. And that led to a lot of not only debate as to what the composition of Ceres actually was. Was it differentiated? Was it highly porous? Was it full of organics? Is it composed of a lot of water ice? And this led to a lot of debate and interest to the nature of these protoplanets in the main belt, and led to the inception of the Dawn spacecraft. So this image on the right has the family portrait, I like to call it, of main belt asteroids, all the ones we've sent spacecraft to, including a few near-Earth objects, ranging in appropriate scale from the enormous Ceres to the next largest 4 Vesta, Lutetia, all the way down to the tiny asteroid Bennu that was recently visited by OSIRIS-REx. And for those who are involved in astrobiology or planetary science, or have familiar with the results of the Cassini mission, will recognize that Enceladus here is around the same size as Vesta. This is to scale. It is one of the most exciting moons of Saturn because of its famous tiger stripes and plumes that come out of the south polar terrain. So, and this is, I always like to show this in context because this is the size of Enceladus relative to Ceres. So in terms of evolved planetary objects, Ceres is not to be taken lightly. It is truly an interesting, fully formed planet. And to kind of put a little bit of a human perspective on it, I want to go through the history of the discovery of Ceres just because I find it so fascinating. But just in record time, so we know that with the discovery of Uranus in 1781 by Herschel, that really bolstered faith in the Titius-Bode law in the European planetary astronomy community, which kind of predicted where planets should be in our solar system based on regular geometric intervals. But there notably was a planet missing right between Mars and Jupiter. And this led a couple of famous European astronomers, led by Baron von Zach, to form this kind of ragtag group of planet hunters that he called the Celestial Police in 1800, with the goal of finding this missing planet. And they sent out letters to a bunch of astronomers within the greater European area, including this man here in this photo called Giuseppe Piazzi. But he never received his letter at the Observatory of Palermo in Sicily, so naturally it was him who discovered Ceres on January 1st of 1801. But he became so bedriddenly ill within days of this discovery that he couldn't make a follow-up observation and lost it. And because of the limitations of telescopes at the time, could not recapture it and get those series of measurements needed to really determine its orbit. And once the rest of the European astronomers knew of this blunder because he told them, but then immediately told them that he lost it. They really raked him over the coals, and probably one of the first like flaming letter chains between astronomers that I can remember. And then the plot thickens. So Carl Friedrich Gauss, of mathematical fame, developed new mechanics for estimating the orbits of planets. And between these new mathematical developments and concerted effort by European astronomers, almost a year to the day that it was first discovered, on December 31st of 1801, Sirius was rediscovered by Baron von Zach and Heinrich Olbers and forever cemented in the history books. So that's kind of that's the storied history of the first asteroid ever discovered. And this image on the left is kind of what Piazzi might have seen when he first looked through his telescope and found Ceres in 1801. And this is broadly what we came to know of Ceres for the next 200 years. Not a lot changed. It remained this point astronomical object, something to be fancied but not really known that much about. And it wasn't until 2004 that the Hubble Space Telescope, 203 years later, took the first picture that actually resolved Ceres' disk. And we see now we've gone from this purely astronomical object to something that's starting to become a geologic object. We can see a planet. We can see variations on the surface. We can see its spectra. And we know that it has these unusual absorption features at 2.7 and 3.1 microns, suggestive of water and hydrogen and ammonia, things that are common among other asteroids thought to be the sources of carbonaceous chondrite meteorites, these weird, organic, volatile-rich pieces of our solar system that have come down to Earth. And that really enters the Dawn project. We have this protoplanet, this massive object of spectral intrigue that is really unknown, thought to be the remnants of planetary formation, this building block of planets, these things that collide to create the terrestrial planets, left untouched from the beginning of the solar system. And it was Dawn's goal to go out and categorize both Vesta and Ceres as these remnants of planetary formation, to understand their morphology and their geology, and to understand what the building blocks of planets in our solar system were. So Dawn was launched in 2007. It's powered by a 20-meter plus wide solar array, and it was the first science mission to use solar electric propulsion, so through xenon ion thrusters. And our chief engineer always liked to compare them to TIE fighters because they stood as twin ion engines. And he said that Dawn was always better because it had 3. And as part of being a Discovery class mission project, we're kind of like the Spirit Airlines of solar system science. So everything is very focused, very targeted, and done with cost in mind. So Dawn had 3 specific science instruments in addition to its high gain antenna that served as a radio science package. But we had a visible and infrared mapping spectrometer with over 440 channels for mapping surface mineralogy. We had 2 redundant framing cameras contributed by the German Space Agency, which give us our high resolution geospatial information, particularly for geomorphologic mapping and geomorphology and shape model creation through stereotopography. And then finally, there was a gamma ray and neutron detector, which is essentially a big scintillator that sits on the base of the spacecraft and counts neutrons and gamma rays emitted from the surface. And this is really a cool tool because it can use these high energy interactions and the energy spectra of neutrons and gamma rays coming out of the surface, give you an idea of what the nuclear structure of the surface is. So it's a nuclear spectrometer, and it can directly interrogate what the elemental abundances are within about the upper meter of the regolith in Ceres. So after making this launch in 2007, Dawn did a Mars gravity assist and then thrust it out to Vesta, where it spent a little over a year before leaving on a 3-year cruise to Ceres, where it arrived in March of 2015 and spent almost 3.5 years in orbit around Ceres at different levels of altitude before its xenon fuel supply finally ran out on essentially Halloween of 2018. And it's that length of data set that we have available to work with us. So recall back to that picture that Hubble took in 2004. And this is the difference that only 11 years made. And we went from this fuzzy disk, from this point object, to this fully resolved planet, this truly geological we've transformed from an astronomical object to a geological object. And among the many features that we discovered on Ceres, one stood out in particular, and it's this large 100-kilometer diameter crater called Occator that I'm circling with my mouse right now. It's the largest young complex crater on the surface of Ceres, and it houses the infamous bright spots or faculae, which you can start to see in this oblique image. Features that are over 10 times brighter than the average background on Ceres. But beyond Occator, from the global perspective of mapping over 3 years, Dawn discovered Ceres to be ubiquitously covered in ammoniated phyllosilicates. So it's covered in clay minerals, ammoniated and hydrated clay minerals, carbonates, particularly dolomite, calcite, but also more exotic populations like sodium carbonates, nitrite, and a variety of different types of halide salts have also been inferred spectrally. We also noted that unlike Vesta, which has a similar surface gravitational environment, Ceres is populated with a variety of unusual geomorphic features, both from impact cratering to landslides to these large domes and mountains called tholoi, all of which have been associated with unusual abundances of salt, evaporitic or carbonate minerals, or direct detections of water ice on the surface, alluding to an intimate relationship between the geomorphology of the surface and its composition and potential hydrologic past. And remember that gamma ray and neutron detector I was talking about, the GRAND instrument? Whereas at the asteroid Vesta, it discovered hydrogen in the near surface at only trace amounts. At Ceres, we discovered high concentrations, talking about several tens of weight percent, just within the upper meter. And it followed this extremely symmetrical distribution from equator to pole, where it increases as we go towards higher latitudes, where these cool colors represent a reduction in neutron counts, because hydrogen is such a good neutron absorber. Upwards, which led to the estimate that there could be surface saturating ice table, so pore saturating ice within the regolith, that is stable at the surface after about 45 degrees latitude and higher, both in the northern and the southern hemisphere. And it was this combination of factors that led to the decision to target Occator crater for the final extended mission for the Dawn spacecraft. So, with the last reserves of hydrogen that we had, it was decided to place the spacecraft into a highly elliptical orbit, shown to scale here in this image on the left, where we set the periapsis down to as low as 35 kilometers over the surface, which is an extremely low pass for a spacecraft, much lower than Dawn was ever designed to do. And it was put in a synchronous orbit such that every time it came around its periapsis, it was longitudinally co-located over Occator crater. So these deep dives were always associated with Occator to get the maximum spatial coverage for the limited number of orbits that we had. And this resulted in a pan-crater-wide collection of data with image resolution as fine as 3 meters per pixel, as fine or finer than most of the best satellite imagery we have of Earth. And here's an example of what that mosaicing and what those imaging data looked like. We go from this regular prime mission mosaic down to these fine, detailed, high-resolution extended mission data, where each one of these bright speckled feature on top of this bright massif that we've zoomed in on this red square is about the size of a large 12-passenger van. So that's the level of detail that we were able to get out of the information from the final extended mission at Dawn. So, let's get right into talking about Occator and the interesting geology and the story thereof. And part of the rationale for deciding why to focus on Occator for this final extended mission for Dawn was its geologic uniqueness on the surface. So I've already mentioned the bright deposits and the faculae, But not only was this a place where we have these uniquely large deposits of bright material not seen anywhere else on the surface of Ceres, which is otherwise largely homogeneous, but we have the highest abundance of geologically fresh occurring landforms and the highest diversity of geomorphic terrains of any place on Ceres, all within this young complex crater that's around 20 million years old or less based off of crater counting model ages. There was also some formative work done by Tim Bowling that thermodynamically showed that the impact at typical impact velocities at Ceres of around 5 kilometers per second could create a persistent thermal anomaly and melt significant volumes of water ice in the subsurface and have them be sustained for hundreds of thousands to potentially a million years at depth. And this really launched the investigation into what the geologic history of Occator really was. So this is some work done by a colleague of mine, Jennifer Scully at JPL, that was recently published in a Nature Communications article. It's the most detailed geologic map of the surface of Occator, including a highlight of its bright faculae deposits in the middle. So this is a lot of detail is put into this geologic map, but the really big punchline here is that a significant amount of the crater floor is covered by these green-hued geologic units. And these green shades are all interpreted to be these lobate material deposits on the floor. And they're all related to these spectral and nuclear signatures that are suggestive of a high degree of water ice in the subsurface. And they were interpreted to be deposited as water-rich impact melt units. And it's on these green units that we see the highest amount of geologic and geomorphic diversity in the floor of Occator, including hosting the entirety of the Venalia facula deposits, these more diffuse deposits on the right-hand side, and surround most of the Cerealia tholus, the largest bright spot in the middle of the crater. And through some clever use of the high-resolution imagery and small-scale impact craters, she was able to estimate what the thickness of these bright material units were in a lot of the occurrences where they exist. And typically, what was found is that in the Venalia facula, they're in the order of a few meters thick, whereas in the central bright spot near the center, they can be greater than 10, upwards of possibly 100 meters thick, based off of just impact penetration data. So here's an oblique view at the central Cerealia faculae, the central bright spot. And from a geomorphological point of view, this is not just a simple deposit of bright material. It's actually a central pit. And that's interesting for a number of reasons. Central pit craters are not particularly common. They exist occasionally on Mars and have been observed on icy satellites in the outer solar system. And this is the first instance in which they were observed on an asteroid. And while the jury's still out on the exact formation mechanism for central pits, the leading hypothesis currently is that for the same mechanisms that form central peaks in complex craters, where we get these elastic rebounds, you can have the same sort of feature occur. However, if the majority of the material that is being uplifted to create a central peak has been melted, such as the case in which underlying ice has been melted by hypervelocity impact into water, then that material has no cohesive strength. Thus, after uplift is finished, rather than being rigid and maintaining its structure, it simply flows back into the subsurface through fractures and porosity that has been created by the impact, and that can lead to the creation of central pits. However, the plot thickens again for Cerealia, because there is a central dome within this central pit that measures nearly 4 kilometers across and over 400 meters tall with these radial fractures, and is the home of the thickest deposits of this bright materia feature. And thanks to Don's mapping spectrometer, we know approximately what the composition of this bright material is. And in Cerealia, it is dominantly sodium carbonate, natrite, over 60% by volume, approximately. We also know that there are significant components of sodium chloride in the form of hydrohalite, nearly 20% by volume inferred from spectral information, and with the remaining 20% being partitioned between trace species, ammonium chloride salts, and ammoniated phyllosilicates. The composition for the more diffuse facula, the Venalia facula, is roughly the same, although there's a noticeable decrease in the concentration of sodium carbonate. So these are the Venalia facula zoomed up. And I've overlain this image on the left as that geologic map again of the units around Cerealia, but I've highlighted the large tectonic fractures that have been noted. So there is a pervasive fracture network throughout the crater as well, mostly emanating from this nexus in the southwestern quadrant. This is actually associated with a topographic high. This is a dome. And then there's these radial fracture trains that lead away from them. Now the main train that leads towards the center of Cerealia facula is deflected just south of the main bright material, but passes right through Venalia faculae. And you can see that in these zoomed in images of this lobate terrain hosting Venalia on the right, where we're looking at these major pit change and fractures that run directly through these diffuse deposits. And here's a particularly insightful image, the sub-image B, that shows this large pit chain running through and dissects some of this bright material. We can see a fresh exposure with some mass wasting in this little tiny ribbon, only a few meters across. And broadly speaking, the Venalia faculae concentration increases as the fracture density increases, suggesting that that they are acting as a possible pathway, transport pathway for whatever fluid or medium could be used to be creating these features. Which brings us to the final geologic interpretation based off of these qualitative observational traits that were noted. So this is the interpreted cross-section of Occator crater in its current form. Whereas we have this exaggerated vertical relief where we have this complex crater with all its characteristic terraces, highly fractured and faulted breccia lens directly beneath it. But then we have these large, flat, smooth, plane-like deposits that have been deposited and are interpreted as these impact melt units, these lobate materials. And they range in variety and texture from smooth and interspersed to hummocky and lobate, with this deep central pit with a central dome in the middle of Cerealia faculae. And in its current form, it's estimated that based off of the crater density ages on top of the innermost faculae, that they postdate the formation of the crater by several million years, implying a protracted event to either produce them or release fluids onto the surface, which were then sublimated and evaporated away, leaving these evaporite-like salt deposits behind. So whereas the initial creation of the crater would have had a pore saturated fluid melt reservoir right beneath it, as that froze from the outside in, we're left with a potential remnant impact-induced melt chamber that exists below Cerealia faculae, possibly, and there's some gravitational evidence to suggest that this low-density area might still exist to this day, and it's possible, although direct evidence is lacking so far from what Don can ascertain, that there is a link between a deeper brine reservoir and what was created by the impact event itself. So, beyond the geologic reconstruction of Occator, there are two geomorphic features of note that I want to focus on for the rest of this talk. And the first is the abundance of those lobate materials, those kind of rock star geologic units in Occator where all of the interesting things is happening. And the first of those I want to focus on are the large-scale geomorphic flows. And this is work that is done in conjunction between myself and Brittany and some colleagues at Johns Hopkins, APL, Deborah Bushkowski, that shows flows associated with impact melt units in Occator crater, and they are ubiquitously present. So this box, this blue box in this image on the left is shown larger here on the right, where you can see this is the terminal flow front for the hummocky low-bait material seen just north of these faculae. And then here's a zoom in on this small little section in this red box down here, where we can see this beautiful example of these really furrowed hummocky flows that are superimposed on top of each other. Now, this harkens back to some work that we did when we first arrived at Ceres. Ceres is no stranger to low-bait deposits and landslides. In fact, it's has one of the highest concentrations of mass wasting features of any object in the solar system, with nearly every crater exhibiting some form of secondary mass wasting. And Brittany and I did a lot of work looking at the global density of these features on Ceres, and found that they generally fall into three archetypes. These kind of thick, bulbous, viscous appearing flows, dubbed type 1. These smoother, longer, run-out, more mobile landslides, dubbed type 2. And then these kind of radial, ephemeral, multi-lobate type flows that emanated from impact craters that are typically associated with fluidized appearing ejecta. Now, what's particularly interesting is that we found that these type 1, these really thick, these hundreds meters thick, concave down, well-determined, discretely margined flows, type 1s, have an increasing abundance as you go from the equator to pole. And they correlate with hydrogen abundance data as observed from the gamma ray and neutron detector. And they also have a lot of morphological features suggestive of types of viscous flows. Now, I'm going to be very careful with my words here because there's been a lot of analogies done in the past to draw these similarities between these types of type 1 flows and periglacial mass wasting features on the Earth like rock glaciers. Now, it's extremely unlikely that flows on Ceres that are these large, thick deposits are behaving in a way that's analogous to rock glaciers. They do have a lot of geomorphic similarities, particularly these lateral furrows, this type of multi-lobate appearance with superimposed lobes, and these thick, discrete, concave down-shaped front toes. Such as this example from Colorado and the Chugach Mountains in Alaska. But beyond just looking similar, they actually behave similar. And when you look at the mobility of these landslides as measured by their drop height to runout length ratios as proxies for this mobility, we see that these type 1 flows, as indicated by these blue triangles, have significantly reduced mobility compared to the more ubiquitously present landslides, both on Ceres, indicated by these yellow dots and red diamonds, but also long runout and standard landslides seen on Mars, Earth, and icy satellites like Iapetus. And these type 1 flows more closely fit in with frozen debris flows, so these Earth X's up here, that are these viscous type appearing deposits in these ground ice rich regions in polar or alpine terrains, such as the examples shown on this panel on the right. So there's evidence that this process is happening both at high latitudes on Ceres and in high concentrations in area where there's refreezing material in Occator. These lobate deposits exist specifically within these lobate material units. And if you recall from the geologic map, those green-hued units were mostly in this horseshoe shape around the southern portion of the crater around the center, which is exactly where the high-resolution and final extended emission gamma ray and neutron data from Dawn found an enrichment of hydrogen within the floor of Occator crater. So this final extended emission data showed that these lobate flows and hummocky deposits are significantly associated with around a 5% weight percent increase in water equivalent hydrogen throughout Occator. And this suggests that there is ice within these flows to depths that are not really any greater than 1 meter within Occator. Which brings me to the final geomorphic topic that I want to cover about Occator. And this is the one that's near and dear to my heart, and we're going to learn a lot more about this in the coming years, hopefully. But the final treat from the extended mission of Dawn and its imaging into Occator was something we didn't expect. We went in specifically trying to look at these bright deposits and uncover the geologic history and understand what fluid reservoirs might exist and what chemical reservoirs might exist in Ceres and on Occator. But thanks to that increased resolution, we were also able to find something that we weren't looking for. And those are these small-scale hills, 100 meters across or less, scattered throughout these lobate deposits on the floor of Occator. And they have an extraordinary similarity to small-scale periglacial hills on Earth called pingos. So pingos are these ice-cored mounds that form in these Arctic and perennially frozen terrains that consist of injected ice or injected pore water or groundwater that then freezes into an ice core that uplifts these hills to heights of tens of meters or more. And these have been hypothesized to exist on Mars, such as the subfigure D over here. But this is the first time outside of the Earth and Mars and on an airless body that similar types of features have been noticed. So pingos can form on Earth in one of two ways, either hydrostatically or hydraulically. So in the case of a hydrostatic pingo, also known as a closed system pingo, you typically start out with an unfrozen region within permafrost called a talus, typically like a thermokarst lake or a body of water, such as like in this first cartoon, subfigure A. And then as you refreeze or the permafrost encroaches and aggregates towards it, it freezes and the pore water is expelled out as ice forms and volumetrically expands. And as that creates this hydrostatic gradient, forcing water towards the center of these unfrozen regions, where eventually they are forced upwards with their path of least resistance, are injected, supercooled, freeze, and form this ice core that eventually uplifts, creating a pingo. And in the case of a hydraulic pingo, or an open system pingo, a similar process is at work, but rather than the pressure being generated by the freezing of a closed system, you have some sort of topographic gradient generally. So groundwater coming in from higher elevations, like on the side of a glacial valley or from a mountain, capped underneath this impermeable permafrost layer, essentially creating artesian conditions where water is then injected through fissures and cracks and freezes, forming a hydraulic pingo ice core at the base of these valleys or between mountains. And once again, here's an illustration of one of my favorite such images of a potential pingo on Ceres. It's about 250 meters across, which is extremely similar to the size of some of the largest pingos on the Earth. So, with that in mind, we collated all of the extended mission Dawn images at around 3 to 5 meters per pixel and went through the entirety of Occator with a fine-tooth comb, looking for any types of anomalous hills that might exist on this floor. And we broadly determined that there were essentially four to five, one's really a subclass, classes of qualitative morphological hills that exist. And those exist were types of hills that appeared simple conical in nature. There were ones that were simple domical in nature. But the distinction there is that instead of being highly peaked, they're more rounded. Then these flat-topped hills come in a couple of varieties. They typically have these broad, flat, plateau-like summits, or can have these linear ridges. Cap rock are typically cliff-forming units on the top. And then these kind of depressed summit mounds are just a variety of conical or domical hills that just have these pits on the top, not too dissimilar from small volcanic cones or the pits and cracks common on the top of pingos. And in total, we noticed there were around 922 of these. And this is a kind of a busy diagram showing all those geologic units again. But the punchline here is, if you think that you can see a concentration of them in specific geologic areas, that your eyes aren't fooling you, you are correct. There's an extreme preference for these hills to associate with the interspersed lobate material, which is this blue geologic unit highlighted on this image of Occator in the back. And just as a type of fractional histogram to drive that point home, nearly 50% of all the identified hills, regardless of morphological classification, were found in this particular unit, with the remainder shown, with the remainder clumped together into these different geologic material units. But we can do more than that. We can do more than just map these hills and find out where they are. We can use the depth and quality of the Dawn dataset through imagery and topography to really get an idea of what the detailed morphometry and morphology of these types of features are, and use that, hopefully, to identify, if not their origin, what their likenesses are across the solar system. So as an extension of this project, we used the Dawn dataset to create detailed digital elevation models of stereo pairs from this extended mission data to cover as many of these hills as possible. And what we noticed was that we could resolve around 78 of these features within the surface floor of Occator in this representative sample shown in the top left-hand image. And then we also wanted to take some metrics of these features, such as what their symmetry looks like, how they're skewed, what their kurtosis, or how their flanks are curved, how steep they are, and what their aspect ratios were. And we want to compare those to common terrestrial examples of hill forms, of discrete hill forms in both Arctic and non-Arctic environments. So what we did is we repeated this exercise where we gathered this information using terrestrial data sets for volcanic cones in Iceland, such as this figure shown in the top right, and additional volcanic cones from regions in the United States, in this case from the San Francisco volcanic field in Arizona. We also looked at over 500 pingos from the highest concentration of pingos on Earth in the Tectonic Peninsula in Canada, and acquired the similar amount of information. So when I say geomorphic information, how we interrogate these hills is by taking these profiles across the tops of these hills, both on Earth and on Ceres, and we gather this linear information like this. And we can collect these along the major and the minor axes to get a proxy for how these hills are behaving in 3 dimensions. And here's an example zoomed up of the type of features that we were examined both on Ceres and on Earth. So these are different types of hill and dome morphologies on Ceres. In the bottom row shows pingos on Earth, and then volcanic cones in Arizona, and then volcanic cones in Iceland. And here's a graphical illustration of what I mean when I'm talking about some of the more unusual morphological metrics. So when in terms of symmetry, it's essentially a measure of how symmetrical a profile is compared to how anti-symmetrical it is. And then we did that using a technique called even-odd decomposition. So essentially you can think of these profiles, such as in subfigure C, being composed of an even function and an odd function. And by weighting those two against each other, we get a measure of its symmetry versus anti-symmetry. Kurtosis is this idea of how tailed the edges of a distribution are. So in this diagram, there's a bunch of different distributions shown with different colored curves, and they all have a different measure of kurtosis. And the important thing to note, of what really the take-home argument here, is that if you look at this just simple box, this purple line, or this kind of ellipse that's been cut off, this blue line, their kurtosis is negative. So the lower your kurtosis, the more abruptly the hill kind of terminates. See, they don't really have a tailed distribution. They just abruptly end. Whereas ones that are protracted and are dragged out towards the edges, those have a higher kurtosis. And then a skewness is just a measure of how much a symmetric distribution leans to one side. So after we collected these metrics for our types of hills on Ceres and on Earth, we can compute using kernel density estimation, which is essentially a non-parametric way of histogramming things to estimate their probability density function. We can estimate those distributions over the range through which those parameters exist. And this image on the right, I've shown that analysis for 4 different metrics. In this case, it's the root mean square maximum slope, flank slope for hills, their symmetry index, that measure of evenness versus oddness, their Fisher-Pearson skewness, so how much they're skewed, and their excess kurtosis, again, that measure of how quickly they terminate. And what's really interesting is that from the statistical derivation of these functions, we see 2 things. One is that, in general, the hills that we observed on Ceres, these black lines, are largely similar in all of our measured metrics to these hydrostatic pingos that were measured in the Tectonic Peninsula, measured by these dashed yellow lines. And the second point is that if we even look at just the terrestrial examples of pingos versus cones, there is a very detectable signal difference between these metrics of pingos and what were measured for volcanic cones, both in maximum flank slope, in symmetry, sorry, my slides keep bouncing forward, so I must have set that up before I started, without realizing it, and both skewness and in kurtosis. And then the final leg of this analysis is, now that we have this abundance of statistical metrics and these estimated distributions, is that we can analyze them together and form an index for how similar these hills on Ceres are morphometrically to these analyzed hills on Earth. So we utilized a Metropolis Hasting style Markov chain Monte Carlo model to look at the metrics that we measured, and under the assumption that the probability that a hill is similar to like a pingo or a cone is proportional to how those metrics line up with those estimated distribution functions, we ran these models. So this is an illustration of kind of the workflow of the Metropolis Hasting algorithm. Essentially, we just pick a random state, and then we propose a transition to a different state, and then based off of the probability or how well that metric lines up with the distribution function of that new state, we accept that change. And by doing this over and over again through a high number of iterations, you can start to approximate what this complex probability function is for these different states of observables. And that's what's represented in this final state. So for each of those hills that we measured all of those properties of, we ran this model through for 10 to the 7 iterations for each hill. And we looked at 4 possibilities. So we compared the morphology of the Syrian hills to those of the pingos. We compared them to those of the Icelandic cones. We compared those to those of the San Francisco cones. And if they had a very low similarity to any of them, there was this generic other bucket that accounted for features that are dissimilar to all our investigated landforms. And the results of this analysis were that the overwhelming majority of these features that we were able to resolve in Occator had a majority or plurality pingo-like affinity. So they were more like a pingo morphometrically than they were of any type of terrestrial volcanic cone, by a ratio of about 2 to 1. So while this is not an indication that they are genetically analogous to pingos, this is a quantifiable step that shows that they are, at least they appear, physically similar to pingos. Which is really laying the groundwork for what we want to do in the future. So just to wrap up, I remember last year I gave an Exploragens colloquium talk about understanding the distribution of these potential pingo-like features on Ceres, and how we wanted to go and use geophysics to better constrain what the hydrology of pingos were at depth, to better inform how we should go out and do planetary science in potentially periglacial terrains on Mars and on Ceres and other planets. And that project was called PingoStar. So we were very fortunate that PingoStar was selected as a program to be conducted. So this is something that Brittany and I and our team are working towards this year and the year after that with bated breath. And much of the past few months that we've been up to has been spent organizing a field campaign for this spring to go look at pingos and image them using 3 different geophysical techniques. So we're focusing on ground penetrating radar to understand the structure of pingos at depth. So just this is a schematic overview of how ground penetrating radar works. We just send electromagnetic waves into the surface, and on permittivity contrasts, you get reflectors, and it's very good at detecting interfaces between high contrast layers such as water and ice and unfrozen soils. We're also looking at using resistivity methods to understand what the structure of these features are. In particular, we want to use capacitive resistivity, which is a technique that you don't have to drive stakes into the ground. Instead, you just have these transmitters, such as this handsome gentleman here is dragging this long line of receivers and transmitters that act as antennae that create currents in the ground that then can be received. And depending on the spacing of the receiver with the transmitter, you get this cross-section at depth of what the resistivity of the soil is. And finally, we want to use electromagnetic methods, such as passive magnetotelluric or active transient electromagnetic soundings, to estimate what the deep structure is and understand where these conductive layers are, such as sub-Pingo water lenses are and how they connect with each other. And this is an example of a sounding profile using active electromagnetics, or what a passive electromagnetic sounding profile looks like for magnetotellurics. And the final goal of this is twofold. One is we want to create the first and best three-dimensional geophysical look at pingos of different varieties in both the Alaskan Arctic and the Canadian Arctic over the next 3 years. These are perennially understudied landforms that have never really been given more than a single GPR section or single resistivity survey. And we want to go out there, and we're planning to collect a multitude of cross-sections to build these really detailed 3D profiles to understand what they are at depth and how to prepare us for planning to explore them on planets in the near future, which is the second goal of PingoStar, beyond doing Pingo science and Arctic hydrology, is to test these geophysical methods to understand what their best synergies are and their difficulties in deployment, and prepare the next generation of planetary geophysicists to carry out these experiments on the surfaces throughout the solar system. So to conclude, I want to say that what we learned about Ceres from our final extended mission at Occator is that we know now that Ceres has an ice-rich crust that's ubiquitously covered in these carbonates, including exotic carbonates. And these faculae are chemically similar to evaporites in alkaline environments and soda lakes on the Earth. And we know that the small hills and fractures and faculae in Occator imply a liquid water and hydrologic origin that has been active into the recent past, as early as just a few million years ago. And that geophysical investigations of these potential analog environments on the Earth will not only tell us more about these features on Mars and Ceres, but prepare for their exploration across the solar system. So here's just Ceres at around approximately 46% water by volume, is the most water-rich object in the inner solar system. And here's just a recapitulation of how similar those chemistries are to those soda lakes on Earth. And it's also similar to what we see in the plumes of Enceladus today. Something that Ceres can tell us not only of hydrologic processes in the solar system, but of our own Earth and how water interacts throughout the solar system and throughout time. And we know, and here's just a recap on the geophysics of Ceres and its moment of inertia factor. And once again showing the carbon content and nitrogen. So this is our drive home slide of why Ceres is interesting and why we should go back to it. And with that, I'd like to take any questions.
Hooray! Lovely job, Kai.